Welcome, everybody. It is my pleasure to introduce David Sanders today. I will be quick because we're already a little bit late, but he moved around a bit between mathematics, physics, applied mathematics. He started out in Cambridge, went to Brussels, back to Warwick, and then he went to UNAM in Mexico City. He has made contributions in the mathematics of billiards, but more generally in dynamical systems, both deterministic but also random walks. And lately he has also been working a lot. He has been one of the main developers of the IntervalArithmetic package in Julia, and that is part of what he's presenting today. So his talk is about finding 1,000,000 roots in 1 second. Well, the 1 second we'll have to see because there were some, the computer was a bit slow, but we'll see. Okay, David, take it away.
Okay, well, of course, I'd like to start by thanking the organizers very much for the opportunity to speak here, and of course for running this fantastic seminar series in difficult circumstances. So So yeah, I'd like to talk about our work. This is joint work with Luis Benet, my colleague at UNAM, the National University of Mexico, on tooling. So this is a bit different from most of the seminars that we've had in the series. I'm going to talk about the tools that we've been developing, which of course are very important for any kind of computer-assisted proof. And in particular, we've been developing these packages in the Julia language, and I'll basically try to show why the Julia is so nice for these kind of tools. And in particular, as Yambao said, I will try to show how we get excellent performance. So, okay, so, which is the subtitle of the talk. So we have tools which are both usable and at the same time high performance, written in the Julia language for both basic interval arithmetic and all of the various methods such as root finding and global optimization that are built on top of those methods. It's all free and open source software, and we have a new web page, Julia Intervals web page here, where you can have links to you can see which packages we have. So interval arithmetic, interval root finding, optimization, constraint programming. I'll mention most of these, and there are various tutorials about those packages and how to install the software, etc. Okay. Oh, come on. Sorry. I'm having quite a lot of technical issues, so I don't understand why I've just lost my... Okay, sorry. What is going on? Sorry about this. Yeah, in particular, my plots for some reason are having trouble displaying themselves. Hopefully that might sort itself out. Okay, try again. So let's think about what kind of properties we need from an interval arithmetic package, or indeed from any scientific computing software. We want to be, I really think it's very important to be able to use the software interactively. Once you've gone to an interactive language, it's difficult to go back to just having a compiled language where you can't actually interact with your code. We want to be able to write expressive and compact code with no so-called boilerplate. I don't want to have to repeat myself with useless bits of code that many languages require you to do. But we still want it to be high performance. And the code itself should be easy to write and read. It should look like mathematics, ideally, right? If we're mathematicians, we want the code to look as close to mathematics as possible. And if not, at least pseudocode as we would write in a paper. We want it to be generic so that I can write, code that runs for real numbers and intervals without actually changing my code. And I want to be able to reuse work that other people have already done. you know, if I don't want to rewrite an automatic differentiation package if that already exists. And the software itself should be easy to install, but it should also be, in my opinion, open source free software. I think that's really important for science to progress, that, you know, people can actually see what you're doing and modify it and, you know, create something together. And along with that, the source code should, you know, if we write an academic paper, the source code should be published with the paper. That's a strong belief of mine. And that requires us to be able to reproduce the exact computational environment that we have. So those are some, you know, sort of lofty goals for any kind of scientific code. So let's think about the standard workflow that people often use. You might prototype your code in a high-level language like MATLAB or Python. And then if you need better performance, you actually end up rewriting the so-called inner loop, the fast calculation, the calculation that needs to be fast in some other language like C++ or Fortran. So this leads to what some people call the two-language problem. And it's just really not a good use of our time to be rewriting like that. So that's why we ended up using Julia. So Julia is a programming language that was released 9 years ago that was designed for technical scientific computing. And so that the creators of Julia in this manifesto that they published said, we are greedy. We want it all in the same, you know, same environment, same language. We want it to be interactive, but also fast. And they based their language on multiple dispatch, which I'll mention later. And that actually turns out to be quite natural for mathematics. So basically, if you have the cosine function, you want to be able to take cosine of a number and cosine of an interval with the same kind of, just by writing cos again, right? And so now we will be able to prototype and get high performance in a single language, and that reduces cognitive overhead. And so, you know, Julia actually ticks all of the boxes on this list. And I'm not going to go through this in detail. I'm going to show that during the presentation, hopefully. And so, you know, each of these individual requirements is available in other packages, but I believe that our work is, you know, actually provides all of these in one package. Okay, so yes. So basically, what am I going to talk about? Some features of the packages that we've developed showing interactivity and performance concerns. I'm going to talk a bit about the implementation of this foundational package, which is IntervalArithmetic.jl, and then mention a few applications, sort of root finding, global optimization, and Taylor integration, and then constraint programming, for which we have a new kind of approach. I believe it's new via code generation. And then finally, I'll talk about the subtitle of the talk, which is how to parallelize interval calculations on the GPU or graphics card. Okay, so how do you install Julia? You download it from this site, and then Julia has a built-in package manager, and it's easy to just install the interval arithmetic package with this couple of commands. You do that once, and then every time you need the interval arithmetic package in a session, you're just going to put using interval arithmetic, and it will load in the function definitions. So let's look at some features of this package. So you can define an interval with this ... syntax. And yeah, okay, so everything seems to be working great. So, so this creates an object, a new type of object, which is called an interval, and it has float 64 inside. These are 64-bit floating point numbers. And I can do operations with standard syntax like plus, times, etc. So let's define two different versions of the square function. You know, one where we multiply and one where we actually take the square. And we see that the results are different as we expect, because here we have the dependency effect, and here we don't. And I'm actually working in a notebook called Pluto, a new notebook for Julia, which is reactive. So if I change this interval, we see that all of these answers change immediately. And so that's a very nice way to, you know, investigate what happens when you change inputs in your code. And I can use big float intervals. So if I just wrap this interval in the big function, now I'm working with big floats, and we see that it tells you what precision, that's the number of bits of the mantissa in the multiple precision floating point number using MPFR inside. Okay, so let's see if this is going to work. So I'll come back to that. This is supposed to be a visualization of the interval Newton method that's interactive. Okay, so, okay, yeah, that works, great. So here is a function that I want to find some roots of. And what am I going to do? I'm going to, so I have sliders Pluto allows me to have sliders and yeah. Sorry. So apparently the plots are now working. This is good news. So I can change this sort of midpoint. And at that midpoint, what am I doing? I'm evaluating the derivative over this whole interval in the interval Newton method. And then I'm drawing lines at all the possible slopes. And then I'm going to intersect those lines with the x-axis. So that, in this case, produces these two intervals. And now the next stage, I'm going to separately consider those two intervals and repeat the process. And so there's these intersections must contain all of the roots. So I just keep on intersecting that. And we get these sort of this set of intervals that's gradually converging on, well, actually very quickly converging on towards all of the roots. Let me just speed that up a bit. And we see that it indeed is finding all of these roots. And here it's going to correctly find those roots over there. So this is, you can make very nice interactive visualizations pretty easily. And that's great for teaching, but also for research. So how's the performance? So let's think about calculating stationary points, for example. Here is the Griewank function, a pretty famous function in global optimization. It's basically a quadratic with some high frequency oscillations. And so if we want to find the stationary points of that function, we need to calculate the roots of the gradient of it. So how easy is it to do that in our packages? Well, first of all, let's define the function, which we can do in a pretty compact syntax like this. So here we're summing the absolute square of each element of the vector x. And here we're taking the product of cos x component I divided by square root of I. And we have this sort of for loop. This is basically some kind of array comprehension. And all we need to do is load in the interval root finding package and then take roots of the gradient of g. So if you think about it, g is a function, and this gradient operator is taking in a function and producing another function. So it's a higher order function. And you can use Unicode syntax in Julia like this gradient operator. And then it will return a list of boxes. So here's an interval box in 2 dimensions, and it will tell you if the interval Newton method or Kravchuk method could find that there was a unique root in there. So how fast is this actually? So here's a comparison with Intellab, so a timing comparison. I have to say that we have to take all of these timings with a big grain of salt. We might have, it's difficult to compare, the parameters of the algorithm, and Intellab is, a great piece of software which revolutionized the field of interval arithmetic by making it indeed easy to use. And it suffers from the fact that MATLAB has this performance overhead due to being an interpreted language, which I believe has become less of a problem over time. But still, here's a comparison with the results reported by Professor Hump in his 2018 paper. And so basically we have something like so maybe my computer is a bit faster. So let's say we have something like a factor of 100 speed up over Intellab. But as I said, we have to take that with a grain of salt. So here what we're doing is computing stationary points of the 2-dimensional Griewank function in a box. And there are 200,000 of those roots. And we can do that in 11 seconds on the CPU. On this laptop, which is a relatively recent laptop. And global optimization of the Griewank function in 50 dimensions, which turns out to be relatively easy with interval methods. Again, we do that in 0.2 seconds or something. So I have to say that these times are after compilation. So in Julia, compilation times can be a problem. That's being worked on. But yeah. Okay, so another great feature of Julia is composability, by which I mean the ability to interact with other packages. So, as I mentioned, automatic differentiation is something we need for this interval Newton method. We're using that. And so we're going to let's load in this forward diff package for forward mode automatic differentiation, which somebody else wrote without any knowledge of intervals. But I can just take their Hessian function, which operates on a function, and when you feed it a vector, now I want to feed it this object of type interval box. And that interval box actually contains inside, it's just a wrapper around a vector of intervals. So I'm just going to extract a vector from that interval box. And I'm basically adding a new method or version of this function with the same name. And I can just attach that to my pre-existing code that I'm bringing in from this forward diff package. And so here I'm applying, for example, this Hessian function to the Griewank function with an interval box, and we see that indeed I get a matrix of intervals out. And so this matrix is not something that, again, not something that I wrote. I don't want to be writing a matrix package. I want to use the matrix package that Julia already has. And in this case, it's a package called static arrays for small matrices. And now what can I do? I can actually take a big float version of that matrix and then take the inverse. And again, I haven't had to write any of this code. So there's a generic inverse for generic matrices written already in Julia, which basically does the sort of standard textbook algorithm, and it just works on intervals. Of course, it might be possible to make a better version for interval matrices, more performant, or which gives smaller bounds. And in that case, you can just sort of extend this method with a special version just for interval matrices. Okay, so then I can go on to classify the stationary points of my function using the Hessian, and then I can plot them. Okay. So let's look at the interval arithmetic package briefly. So it's an implementation from scratch with a liberal software license. And basically, because we decided to use that license, we decided that we couldn't actually really look at the code of any other packages. So it's really a re-implementation from scratch. And things like the sine function and cosine are actually difficult to implement, and I couldn't find very much information about that in the literature. And we believe that it has comparable performance with state-of-the-art libraries in other languages. It's written totally in Julia, except for a wrapper for the crlibm library for correct rounding. And it is almost conformant with this IEEE 1788 standard document for interval packages. In particular, it passes this very nice test suite that has a lot of, kind of edge case tests, in particular, for interval packages written by Marco Nehmeyer and then modified by Oliver Heimlich, who helped us get it running with Julia. Okay. So how do we create intervals? There are a couple of ways. You just use this interval function, but there's an issue about are the endpoints included or not when we do that, and there are different ways that you can create intervals to include the endpoints or not. So I do need to talk about rounding because, of course, it's a key point in any interval arithmetic library. So if I just take exponential of 0.5, I'm using the standard built-in Julia exponential, and that gives us faithful rounding. So it gives us one of the two neighboring floating point numbers for the true real number exponential of 0.5. So by the way, okay. So let's just take the opportunity to, suppose I do cos of 0.5 and I do at which of that. That tells me which version of cos am I calling. In this case, I'm calling cos of a floating point number with 64 bits. And if I click on this link, it will actually take me to the line in the source code of Julia where that function is defined in Julia. And so in particular, if I'm over 4 of 0, then can you still hear me?
Yes.
Yes, we still hear you.
Okay, then what it's going to do is call this other function called cos kernel. So let's scroll down and see, here's the definition of cos kernel. I'm having some weird microphone issue now. Let me hope that goes away. So here's cos kernel, and we see that exactly what is it doing? It's just evaluating a polynomial, and here are some coefficients that it's using. But the point is that it's written completely in Julia. So this was actually translated from C a couple of years ago into Julia, and it runs as fast or faster than the C code. Okay, so for correct rounding, if we want correct rounding, we use Professor Kashiwagi's version of error-free arithmetic for arithmetic operations, and the crlibm library for exponential and other transcendental functions. But actually, maybe we don't even want correct rounding. Do we need correct rounding? That's the correct rounding has been a big theme in the community, but actually all I need is a valid inclusion. So I don't know if there's I couldn't find a name for this. Let's call it valid rounding, where I just take previous float and next float of the result of my standard, usual function that for example, from Julia, as long as that function is actually giving me faithful rounding. And I can use multiple dispatch in Julia to choose which version of rounding I want to use. So what is multiple dispatch? It just means that I'm going to, plus is just another function in Julia, and I'm going to take whichever I'm going to, there's different versions of or methods of plus, and I'll choose the one that is given by the types of all of the arguments. So here I'm changing, both the rounding type and the rounding direction, the rounding type and the rounding direction, and it's choosing different versions of the function depending on those. And the whole of Julia is built around this kind of multiple dispatch, and that turns out to be perfect, as I said, for mathematical code. Okay, so another really nice feature of Julia is metaprogramming. So the ability to actually manipulate code. So I can, so this, so I can write x of 0.5, comma, round down, to get the rounded down version of the exponential of 0.5. So I'm adding this extra argument inside, but that's kind of ugly. Maybe I don't want to do that. I just want to write x of 0.5 and then tell it, oh, but I wanted that to be rounded down somehow. And I can do that with this macro, at round down. So at means a macro, and that is something that actually allows us to modify code. So when I do this at round down of this piece of code, it literally takes the unevaluated code before calculating the exponential. It just treats it as a sort of expression that I can modify. And in particular, I can insert this down in here. So as an example of that, if I take pi to the power pi, it's going to use the 64-bit floating point value of pi in the calculation. But if I wrap that in this at interval macro, what it does is actually goes inside and surrounds each of these pi's by a conversion to an interval. And so here you can see what's happening. It's sort of wrapping it in this thing to convert that pi to an interval automatically. And so as an example of that, I wrote for this talk a new macro called @evaluate, which takes an expression and an optional accuracy, relative accuracy, and it just keeps doubling the precision until it evaluates until you get that relative accuracy in the resulting interval. And so here you can see that I took this nice example from Frederick Johansson's paper on his beautiful ARB package, which is also available from Julia, by the way, and you can use it interactively, of course. So here, we're taking sine of pi plus some very small quantity, and so it's close to 0. And we just keep doubling the precision, and it turns out we need 16,000 bits of precision to get the correct answer. Okay, so let me talk a little bit about how Julia actually manages to do this, to make things fast, basically. So how do you actually define an interval in Julia? You can do it like this. You're making a new struct, or can think of a class in other languages. So it's basically an object with an inf and a sup, which are both of some type t, and we're restricting t to be a subtype of real. And then I can just create an object by calling that a function with that same name, a constructor. And you can see that Julia automatically realized that I'm calling this function with integers. If I call it with floats instead, I get, so here I'm creating an interval with floating point numbers inside, and again, Julia correctly parameterizes the result. So this code is actually going to be compiled. So Julia is a compiled language. That's how it was designed. And that's why it's able to do things that languages like Python struggle to do, because it was really designed from the get-go, from the start, to be compilable easily. And to do so, it needs to assign a type to each object. But that's actually done automatically via type inference. So we can see that. So when I take my two intervals, which are intervals with integers inside, what does it actually do internally? It takes, it actually sort of rewrites this into lower level Julia code, and then tries to infer the type, tries to deduce the type of each quantity in the code. So here I'm extracting the inf field or attribute of my object x, and it knows, oh, that's an integer, and so is y, and now I have to add those together, and so I'm going to call this addInt function. Whereas if I were to call this, if I were to add instead my two floating point numbers, my two floating point intervals together, then I would get, now it knows, oh, I have to call this different function called addFloat. And so there's a whole pipeline that Julia is following from your high-level code down to machine code. And here is the machine code. This is the machine code that Julia produces. And you don't have to know anything about machine code to realize that that is a very small piece of code. So it has compiled this complicated, type being added, and then it's gone through a whole sequence of operations to get to a very compact piece of code. And that's why Julia can be fast. And there's this very nice package, benchmark tools, that enables me to actually check how fast is this operation. So if I do add benchmark of this operation, you have to use this slightly strange syntax. Then it returns an object which contains information about the benchmarking. So it's basically running this operation 10,000 times and taking some statistics of how fast each operation occurred. So you'll notice that in my definition of my sum of intervals, I had no rounding at all. And so this is not a valid interval operation. So I need to add some kind of rounding. But as soon as you add rounding, you can see that the amount of code produced here just balloons, just becomes huge. And it takes much longer. And that is, of course, the key problem of interval arithmetic, really, is the rounding. And so we're always in search of faster ways to do rounding. But you can see that we have a very, very easy way now to actually experiment with that. So suppose I define, this other version of plus where I do include rounding. Then here's the code that results from that. Okay, it doesn't work. Sorry. Okay, let's skip over that. But I see. Yeah. So you can see that now the code is quite a lot longer. And when I do the benchmarking, okay, anyway, yeah, sorry. Okay, when I do the benchmarking, okay, yes, let's leave it. But the point is that I can easily modify the code and it immediately gets compiled and then I can benchmark. And so I have this very, very tight loop to modify and change and see what the result is in terms of performance, if I'm interested in developing a faster library. So yeah, over the last couple of years, our focus has really been on speed, but with the previous work on correctness, and so every change that goes into the code base is automatically tested against this ITF 1788 library. Okay, so now that we have an interval arithmetic library, we can build on top of it interval methods. So for example, how do I do the interval Newton algorithm? So here's a two-dimensional function. Here's a two-dimensional box. I just, again, use the Jacobian function from the forward diff package. I define my interval Newton operator in the standard way, except for this interesting backslash. So that is the same backslash as MATLAB, if you know MATLAB, which is solve the linear system J times X equals F of M. And so that turns out to be, it's mathematically equivalent to multiplying the inverse matrix by this vector, but not computationally equivalent. And we actually, I believe we now have our own definition of backslash in our library, but we could actually work that out by using Julia's introspection capabilities, where which version of backslash is it calling? And so, since the Newton method gives me the Newton operator applied to this interval, gives me something that's contained in my interval, that means that I have a root, and then I can just zoom in, but let's do that in big float, right? So I have, since my interval root finding, since the code that I just wrote is generic, it does not assume that I have an interval of any particular kind. I can just put in a different kind of interval. So instead of floating point, again, I'm going to use big floats. And now I have the root to an accuracy of 10 to the minus 77. Without me doing any extra work, that's the point. So the code that I'm writing, I tried to make it generic and just leverage Julia's capabilities to make it work on all kinds of different objects. Okay, so global optimization is a key application of interval arithmetic, of course. So here's some pseudocode for the Morse-Gelbo algorithm. At least it looks like pseudocode. It looks quite a lot like mathematics because I've chosen to use these sort of nice mathematical symbols, but this is actually real Julia code. So this is the entire Morse-Gelbo algorithm in a few lines, and we can easily run it on some one-dimensional function. So this is an anonymous function, the function that sends x to x squared minus 2 all squared, and it returns the global minimum, an interval containing the global minimum, and a list of intervals that contain the minimizers of the function. But again, I have not specified the type of x, and so I can just do the same thing with exactly the same code without any modification in higher dimension as well. Excuse me. So if now I define the Rosenbrock function, for example, now I can just call the same simple minimize function on the Rosenbrock function, and it also works perfectly. Okay. And again, I can use union operators and containment operators in my code. So here's a nice visualization again for teaching purposes. So of this branch and bound Morse-Gelbo type algorithm. So the green horizontal line is the upper bound of the global minimum, and the red box is the one that I'm currently looking at. So I'm going to take each box and bisect it. So there I bisected it, and now I'm looking at this half. And when I evaluate at the midpoint of the box, it sends me down to, I realize that there is a lower version, a lower point on the function there. And so I'm going to drop down my global minimum upper bound to that height. And I keep bisecting until I reach a box which is totally above the current global minimum. And then of course I know that the global minimum cannot be in that box, and so I remove it. And so you get this sort of nice visualization where everything starts accumulating around these 2 points, these 2 local minima, which look like global minima. But it turns out that if you carry on with the algorithm, then it discovers that there's this small piece of function over here, which is actually lower than those. And so it removes all of the boxes there and concentrates around that low global minimum there. And so, this is all written, again, with using the packages. And of course, doing the visualization is a bit complicated, but, it's relatively easy to do. So we have a package that Luis has been developing mainly for Taylor models using another package that we developed previously, which is TaylorSeries.jl. And I had to remove it from here, so because it was causing some problems. So let me just see if I can load that up in the meantime, and please remind me at the end to come back and show you that, because it's quite nice. Okay, so and then we have a collaboration on reachability analysis with Marcelo Forets and Christian Schilling, which can use Taylor models inside to give guaranteed validated integration for ODEs, for example. So I'd like to talk about constraint programming. This is something I've been working on for the last couple of years. In particular, this code generation approach. So suppose we want to find this set x squared plus y squared contained in some interval. We're going to use constraint satisfaction techniques, in particular the forward-backward contractor, also called HC4 revise. And this actually requires access to the syntax tree of the expression. So here's the syntax tree. You can plot it with, visualize with a package I wrote called TreeView. So literally, this expression x squared plus y squared decomposes as the sum of the power of x and 2 with the power of y and 2. And so how does this forward backward contractor work? We're actually going to start with information on the initial box that we're interested in, and we're going to try and contract it by removing pieces that we can prove are not contained inside this constraint set or feasible set. And the way we're going to do that is by introducing new variables at the nodes and then propagating information up and down the tree. So first of all, we're going to introduce these new variables at the nodes. So a is x squared, b is y squared, and c is a plus b. We're starting off with no information. So x and y are the whole plane. So I'm starting off with the whole plane, and I want to find the region that satisfies this x squared plus y squared is contained inside this set omega, which is this interval 0.5 to 1. And so then I'm going to define omega, my set, to be 0.5 to 1. And now I'm going to intersect that set with the current value of c. So c being a plus b is the quantity of interest, x squared plus y squared. And so I'm only interested in those values which lie in this set. So I'm taking the intersection. And now I'm going to propagate that information back down the tree. And so, for example, the new value of a, well, a was defined such that, or c is defined such that c is a plus b. And so a is c minus b. So I'm going to take the intersection of a with c prime, the new value of c minus the old value of b. And we can see that that reduces down very much, contracts the possible values of a. So before, I actually had 0 to infinity for a. Value of a is 0 to infinity because I'm squaring, a real number. And now it's been reduced to 0 to 1. Approximately 1. And finally, x is the square root. I have a equals x squared, and hence x is the square root of a. So I'm sure most people are familiar with how this contractor works, but in case you're not, I really find it a beautiful argument. But of course, I don't want to, and so the point is that I reduced down to -1 to 1. So I've got rid of the entire plane except for a small box, which exactly contains the disk that we know corresponds to this set, or sorry, the annulus in this point. So it contains the annulus. Okay. So what is the point? The point is that I had to do this by hand. I don't want to do that by hand. So I need to automate it in some way. So the way we're going to do it is by using some kind of symbolic computation. So there's this package called Modeling Toolkit, soon to be symbolics.jl, which enables me to actually define symbolic variables in Julia. So A and B here are literally symbolic objects. So here's A, it's just a symbolic thing. If I do A times A, so the new version of the package would simplify that to A squared. And then, so if I now define some normal Julia function, then usually it's difficult or impossible to go inside that function and extract, understand what it does. But I can, by passing these symbolic objects into the function, I can sort of trace through the function and get a symbolic version of that function, actually. So for example, if you have some other code that produced some coefficients or some function, I can hopefully put my symbolic objects through that to get a symbolic representation of the function that you're then interested in, for example, optimizing. And so, for example, the constraint could be that this symbolic thing is less than 1, and that gives me a symbolic version of the constraint. And now I have my interval constraint programming package where I'm going to define this object contractor. I'm going to pass in these variables a and b and this expression that I'm interested in, HAB. And that actually gives me a sort of contractor object that knows how to do this operation that we just did by hand. And when I apply it to the right interval, it does indeed contract the whole plane. Here's the whole plane, minus infinity to infinity in 2 dimensions, and it contracted it down to this box. Okay, so what I'm going to do is actually code generation. So usually what people do is build this tree in memory, and they move these intervals, they sort of traverse the tree in memory, moving up and down. And that is actually what I was told I should do when I started working on this. But I had already actually gone down this route of writing code for the operations. So here is the automatically generated code, right? So this C is this contractor object I just created. And you can see inside what it has is this piece of code that it automatically generated. So it's doing exactly what I did. A squared, this was x squared, y squared, and it's introducing new variables. And then on the way back is calling these reverse functions that are part of the IEEE 1788 standard. But again, it's, you know, difficult to get information about how to implement them. There are a couple of papers. And so these reverse functions are the ones that do this A intersect C minus B operation. And it's all automatically generated. If I change, you know, this constraint here, hopefully to be cubed or something, all of these things should automatically update. You can see that now I don't contract the box enough in one dimension, but you can see that now the code here actually all changed, right? So automatically it's generating this code. And then on top of that, we have a domain-specific language for constraints. So instead of having to specify the constraint in this way as, you know, I have to pass in the variables, I have to pass in the expression, I just write it in this very natural declarative syntax at constraint. And then, you know, I want this expression to lie in this interval. And then once you've specified the constraints, there's this pave function that will basically do a branch and contract algorithm. So we'll literally split up the space into boxes and try and prove that the boxes are inside or outside the constraint set. So this at constraint is actually generating a separator object as introduced by Luc Jeanlin and his group. So this is the result. And I'm hooking into the Julia plotting library plots.jl using a so-called plot recipe, which makes it very easy to plot your own objects. So for example, here's, you know, I've just invented some curves, and then I can easily find the intersection of these two curves, for example, by just taking the intersection of these two separators defined using this intersection symbol. And I can also, of course, use the interactivity in Pluto to do that. You know, so here I'm changing the tolerance, the size of the boxes. So the white has been proved to be outside the constraint set. The blue is totally inside, and on the boundary there's this pink set that I can't prove anything about. And it's all interactive and quite fast. I think it can be even faster. It needs some work. Okay. And yeah, so Julia is actually compiling the generated code into a usual Julia function that I can then use with some restrictions. So finally, I'd like to talk about very recent work in progress that's not yet published or not yet even available, except on my computer, basically, which is parallel interval methods. So how can we do, you know, run interval methods in parallel, in particular on the GPU, which is a graphics card that's something like this size that fits in your desktop computer and has up to 5,000 mini processors in it, which you can use in parallel, literally. So you can, yeah. So this is joint work with Alan Edelman, my host at the Julia Lab at MIT, where I'm a visiting professor, and Valentin Churabi, his PhD student. So what is the goal? Well, algorithms like branch and bound want to evaluate the function over many boxes, but you know, each of those evaluations is totally independent, so they could be run in parallel. In other words, they could be run by different processors at the same time in different places. And there are various ways to do that. So on your laptop these days, you probably have multiple cores, multiple bits of CPU, and they share memory. And so you could want to run the calculation on all of your, say, 6 cores on your machine, and hopefully that should be 6 times faster. Or you might have a cluster of computers or a real supercomputer with separate, you know, physical processors that are joined by some fast interconnect. Or you might have one of these GPUs. And so Julia has various packages to do all of these kinds of parallel processing, and the facilities for that are constantly improving, pushed in particular by the Julia Lab and other places. So, so if we think about what an algorithm should look like on the GPU, well, we want vectorization. So what is vectorization? As I said, a GPU contains many processors, and the way that they're designed for efficiency, they must run the same code on different data. So they literally, you know, different sort of mini processors need to be running exactly the same sequence of instructions, at least within some sub-block of the GPU hardware. And so it's actually natural to think of this in these vectorized ways. So what do I mean by that? I mean that given a vector of intervals, we want to apply a function element by element, the same function to all the elements of a vector. And so in Julia, we have this nice syntax f dot of v for that. operation for any function f and any vector v. So in Python and MATLAB, for example, and R, you need to do this. You need to write code in this way in order to, quote, make it fast, by which we actually mean run code that's not at all written in Python or MATLAB. It's actually going to call a C function, a function written in C or C++ under the hood. But in Julia, that's not the case at all. This is just a sort of nice syntax for a for loop. But a for loop on a GPU is not what you want, because a for loop is the sort of this linear thing that moves one by one through the vector. Rather now we want to really, actually, the hardware is going to process everything all at once. It's a sort of vector machine. And so it is natural and indeed even necessary, due to the structure of GPUs, to rewrite our algorithms like this. Now there is a package, kernel abstractions, written by Valentin, which tries to abstract this away. And so you can actually write the same code in Julia to run on the CPU and the GPU, and that's what we're trying to use. So how can I write intervals? So I want to do interval arithmetic on the GPU. And so of course, people have already written interval libraries for the GPU, and that's exactly what I don't want to do. I already have an interval library that I wrote, that I've tested carefully, and I just want to reuse that code, but now compile it to the GPU, and that's what Julia enables. So it enables us to compile a subset of Julia code that satisfies some pretty stringent technical requirements straight to the GPU. Fortunately, intervals are included in those technical requirements, which basically mean that you don't allocate memory on the heap. You only use things that can be allocated on the stack. And so there are these packages, GPU compiler and CUDA.jl, written by Tim Bizard, who's now at Julia Computing, and Valentin, to do this. So that the point is that I don't want to write my, by hand write my interval library. I want to use a generic tool that can generically take any piece of Julia, suitable piece of Julia code and compile it to the GPU. So what does that actually look like? So I don't have, I can try and do a live demo in a minute. I don't have that set up, but basically I'm going to load in the CUDA package. If I have a GPU, I'm going to load in it, which I don't here. I'm going to load in the CUDA package, and then suppose I have a vector of intervals living on the CPU, my normal processor. I'm just going to call this CUArray function. That's going to construct a new array on the GPU where I copy across all the information from my vector that lives on the CPU over to the GPU. And so now I have a vector of intervals that is living on the GPU. And as far as I know, I don't know of any other platforms that enable you to do this. So this literally looks like, yeah, I'm going to actually try and do that. That's going to take a bit. And so then once we have that vector, what do we want to do? We want to do this broadcasting, by which I mean applying this function element by element using this syntax to the GPU, to this array that lives on the GPU. And the amazing thing is, again, that sort of just works sometimes. So then we can use that to do a branch and prune algorithm on the GPU. So what does that look like? So if we have a vector of intervals, called it V, we want to calculate the images by applying this function and then check. So branch and prune is for finding roots. So we want to check whether those the images of those intervals under the function f, the natural interval extension, contain 0 or not. And so here I'm checking if 0 element by element is contained in this vector of images. And that gives me a vector of Booleans, true and falses. And so now comes the difficult step. I have a vector of Booleans which are true and false, and I want to throw away the ones which do not contain 0. So I want to only select the ones that do contain 0. So I want to use something like this syntax, V. So the square brackets are for indexing. So I want to index into my array with a vector of Booleans. And that's something that's very common to do in Julia and other languages. Except that now I'm on the GPU, I don't actually know how to do that because I have to sort of reduce the amount of information in my array. So when we started work on this, this was not implemented in the GPU stack in Julia. And we had to find a way to implement this, which was a fun task. And finally, we managed to do that. And then that means that you can now write this branch and prune algorithm in a vectorized way in sort of 10 lines of Julia in a way that's generic in the sense that it runs on the CPU, but also on the GPU if you just feed in a vector of intervals instead of a vector of on the CPU. Sorry, if you feed in a GPU array instead of a CPU array. Okay, so let me try and show you that. So if I have minus 10 to 10 and I mince it into 20 pieces, that will give me a vector of 20 intervals. And now I'm literally going to do coup array of V. And that gives me an array of 20 intervals, but that now is actually living on the GPU. And as you can see, it's taking a bit of time. That's because it's compiling the relevant function. Okay, and then now let me give that a name, VV, and let me define a normal Julia function, x squared, well, let's say x squared minus 2. And now I'm going to apply that element by element to my VV. And that gives me, so that's going to take a while to compile because what's happening is it's sort of trying to compile this function into GPU code. So the way it does that is that Julia compiles to an intermediate level called LLVM, which all the modern compilers use actually. And then it takes that LLVM code, by which time the point is that all of these objects like intervals have disappeared by then. And so now it's just numbers moving around. And so it takes that code and translates it into similar code, which is then compiled by the NVIDIA compiler to machine code that runs on the GPU. And you can see that this process is actually very slow, unfortunately. So there's a lot of work in the Julia world to speed up these kind of calculations. Okay, so there you are. These are the images. And now I want to know which ones contain 0. So let's do 0 dot in that set. So again, it has to compile that new function. And we can see that we get these zeros. And then there's these couple of ones where the roots are, because the roots are at square root of 2 and minus square root of 2. And so now I should be able to select just those objects. And this is the step that was difficult to, tricky to implement, let's say. And there we go. So we've removed all of the other vectors. And this is happening, in parallel. And I can just scale this up to massive interval vectors because I have, I'm using a reasonably state-of-the-art GPU with 5,000 cores. Okay. Now there's a little small wrinkle just to finish. Which version of, for example, the cosine function should we call? And so that is actually a tricky point that we're still working on as well. Okay, so just to tell you what kind of speeds we can get. So the other day, like 2 days ago, I managed to evaluate the gradient of this two-dimensional Griewank function on the GPU over a vector of intervals. And I got a 1,700 times speed up over one CPU core. So that's really quite spectacular. And without myself really writing almost no actual GPU code. And as I said, that's on this V100 GPU. And so, so I'm proposing as benchmarks, let's find all 10 to the 6 roots of this two-dimensional Griewank function. You actually need to change the factor in the Griewank function to 5,000 in order for there to actually even be 1 million roots. And I could do that in just under 1 second. And I believe that there's still a lot of room for improvement in the actual code. And I believe that this calculation has not been done before to calculate the number of roots, the stationary points, of the three-dimensional Griewank function in the region minus 600 to 600 all cubed. And on the GPU, that runs in 345 seconds. So that would be like something like 8 hours on the CPU with our code. So yeah, okay. So in conclusion, so we have these set of libraries that we're developing from, in Julia, in pure Julia, which are both usable and high performance. And I really would encourage everybody to, we need a lot of help, of course, there's not very many of us. And if you're interested in helping us develop these libraries and improve them in particular with your expertise, that would be very welcome. And this has been discussed a couple of times, but we need some kinds of benchmarks for interval methods with actual code for how to run each benchmark in each interval library. I mean, it's actually very difficult, to go and understand somebody else's library. And so it would be great to just have the same code, the same, problem running in each different library. And we've proposed these new benchmarks for root finding, which are, things that are developing from what Professor Hump has previously done. But we do need some kind of accelerator device to be able to run those, or maybe just a big machine with a lot of cores. Okay, so that's all. Thanks very much for your attention. And apologies.
Thank you very much, David. And I'm happy actually the plots worked in the end.
Yeah.
But, I think it was a big deal to have to be able to see them. But are there any questions? Let's open the floor to questions.
I have a small question. You're using CUDA package, so because I assume it's optimized for NVIDIA graphic cards, but is there any alternative for AMD cards?
Yeah, that's a great question. Yeah, so there is work in progress to generalize this to AMD cards. I think it's almost ready.
Perfect. Thank you.
Yeah, good question. So let me just show you this. So this is the interval constraint programming in 3 dimensions. So here's 2 tori that intersect, and this is using OpenGL from Julia with the amazing Mackie package. And so, for example, I can do things like this. I can just interactively make one of these tori go invisible. So just by changing the code here in Julia, one of the tori disappears, right? And then the other torus can disappear. And then that's the intersection of these 2 tori. It's kind of neat. So this is, a constraint in 3 dimensions, a solid torus, no, not a solid torus, a toroidal annulus, and you can visualize it in 3 dimensions. Okay, calculated with interval constraint programming. And then I wanted to show you the, but yeah, I should let people ask questions.
Oh, sorry.
Go ahead. No. Other questions?
I have a few questions. Does CPU parallelization work, or is work being done?
Oh, yeah, right. So that's good question. Yeah, so that's also work in progress. So I do have a version of root finding. I think mainly root finding so far on the CPU, so parallelized with multiple cores in a on my laptop, say, or on a big machine with many processors. Yeah, that's also work in progress. But again, the tools in Julia for doing that have become a lot better recently. Okay. So yes, there's basically there's various threading, multi-threading packages in Julia now that work very nicely. So basically you can just spawn different tasks, and then those tasks can spawn other tasks, and there's a scheduler that handles it all, so you don't have to worry about that. Mm-hmm. And yeah, it works pretty nicely. I just haven't managed to benchmark the code yet. Yeah.
Okay. Another question. So for the branch and prune, when you're branching, if you go depth first, you don't use a lot of memory. And if you go breadth first, you use a lot of memory.
You're talking about global optimization?
Yeah. And so,
right.
In the example that you did, it looked like you subdivided first and then sent it out to the workers.
Okay, so okay, so here's the, let me come back to that. So that was the Taylor model stuff. So let's see. This code are you talking about?
Yeah, so I guess maybe to ask a specific question, did you do depth first or breadth first for the GPU global optimization?
Oh yeah, great question. So on the GPU, we cannot use the standard tools, right? So here in this global optimization version, I'm using a queue. So that gives me breadth first, I think. Is that right?
Mhm.
Search. But on a GPU, I can't do that. This is a very serial algorithm. So I have to do everything vectorized. And so I'm just literally taking all of the boxes at once and applying everything at once. And then, okay, so at some point you get too many boxes and then you have to prioritize. And then I guess I haven't thought too carefully about how to prioritize the boxes to minimize the number of boxes. Yeah, that's definitely something I need to think about. Yeah, thanks. But yeah, as long as the boxes sort of fit in the GPU memory, you just really want to do everything at once. It's just, you just throw away all the knowledge that people have accumulated about how to do these algorithms because they don't work on the GPU. Is that simple. Of course, people are trying to do, so for example, usually you would use a priority queue for this algorithm. So people have tried to develop, you could want to have some kind of priority queue-like thing on a GPU and try and use that and sort of maybe grab a whole chunk of boxes for each processor separately. And I think there are people who have worked on that kind of data structure for the GPU. I haven't tried to use any of those yet, but yeah, that's definitely a way to go.
Very nice.
Thanks for the question.
Other questions? Or you set yourself up for a question with your Taylor models, I guess, David, because you wanted me to come back to that and ask a question. It's like some kind of time traveling you were doing there. So maybe you can say a few words about it.
Yeah, just briefly. So a Taylor model, I guess people probably know, is a polynomial plus an interval remainder. So we have this package, Taylor models, where you can see that here's again a standard Julia function, and now I'm setting up a Taylor model with some order of approximation. So that's the number of terms in the polynomial in the Taylor series. And then I'm applying, so this is the sort of Taylor model object, and then I'm going to apply that, apply my function to that object, and that gives me this thing which is not a polynomial, right, because it has a sign in it. And then as I change the order, my Taylor model approximation gets better and better. And so there are now various implementations of Taylor models in the literature. But again, this one is, free, open source, high performance, we believe, and easy to use. And, you can use it interactively as I'm trying to show there. So this is, what is a Taylor model? Again, so I have a polynomial in here approximation plus an interval bound that rigorously contains this set. And then we use that in this collaboration with Marcelo and Christian on reachability. So here I'm defining an SEIR model that everybody's familiar with now from the current pandemic situation, unfortunately. So we can easily define a sort of ODE model with some parameters that don't change and some interval bounds on the parameters of the system. And then they have this nice syntax in reachability analysis.jl, which was written by Marcelo and Christian. Here I'm defining the ODE, x prime equals this function that I just defined, and here's the result. So this is a Taylor model calculation, and then with zonotope over approximations to plot the results. And so these are, rigorously containing the solutions of the ODEs for each class in the model. And so yeah,
that's nice.
Yeah. And again, relatively easy to use, and hopefully relatively performant. So this reachability set of tools won the Arch-friendly competition in 2020 for reachability analysis tools.
Okay. So David, there's a question in the chat.
Okay.
Maybe, I don't know, maybe you can have a look because it's
how do you strictly control how the arithmetics are performed, since compiler might change the order of arithmetics, and the result could be different even without interval arithmetics? Parallel computation also has a problem since addition in floating point does not satisfy associativity. Yeah, great question. So, so Julia has a particular Julia is very careful with floating point arithmetic. So, so it does not, it deliberately does not do any operations that are sort of, it does not, it deliberately, well, okay. Yeah. I mean, you basically can specify the order of the operations, the way they're carried out, and Julia will not, I believe, will not change that order. So if you do 0.1 plus 0.2 plus 0.3, sort of with parentheses, then you are specifying the order in which the operations are carried out. And of course, since we have interval arithmetic, we don't actually really care too much because we always have a rigorous bound, however you do the calculation. And so, yeah, Natalie said, results can be different, but they all enclose the sort result. It is good for validity, but not for reproducibility. Yeah, so I haven't actually looked into the reproducibility aspect on different machines. I know that there has been, it's true. Yeah, I do remember that, you know, different versions of Julia, you might get different results. So ideally you would get the same result because, you know, if it's all using IEEE 758, is it, floating point arithmetic. So ideally you would always get the same result on different machines if you do the same calculation. I haven't actually tested that very carefully. I have tested whether the results on the GPU are bitwise identical to the results on the CPU, and they are not because they're using different cosine functions, for example. If you use the same cosine function, which you could do because Julia is defining its cosine function in Julia, so you could literally, and that's what I used to do, you could literally take the Julia function and compile it straight to the GPU instead of using the GPU's built-in cosine function. Then you should get bitwise reproducibility, but I still didn't, and I never got to the bottom of why. So yeah, that is definitely a good point that we do have to be careful about that. But you know, as long as we're using interval arithmetic, we should. Yeah, okay. So I agree. Bitwise reproducibility is something to work on across different machines.
Okay, any
On
more?
the same machine, you always get the same result. So it's not doing anything stochastic with it. You know, it's not changing the rounding, the order of operations in some strange way. How do I manage floating point underflow? So yeah, that's a good question. So do you have a particular example in mind? So we did have a problem with floating point underflow, but I believe that has been sorted out since we now use Professor Kashiwagi's methods, where you flip the order of operations to deal with underflow. I don't know what would be a good example. So so something like 1e minus 300 to 1e minus 300. I want to multiply that by 1e minus 10. So 1e minus 10 just means 10 to the minus 10. No. Yeah, so we do deal correctly with floating point underflow, right? So the minimum floating point number is something like 1e minus 324. And so here we're getting a 0 because we're underflowing. Does that answer your question? But so yeah, there are different rounding modes for the interval arithmetic, as I said, and we can change rounding mode. Currently, that is again work in progress. So currently on this particular version of interval arithmetic, I can, which is the new version, I can configure which type of rounding I use globally by using this interval arithmetic.configure. And I have to remember how exactly to do that. And so we can switch between this correct rounding and this valid rounding that I was talking about. So in valid rounding, I would actually get a small negative number here, which is not ideal, but that's how it has to work if you're doing extra rounding.
Okay. Any remaining questions?
I have a question if we still have time.
Sure, Flora. I will have to say goodbye, but Jay is gonna take over hosting.
Oh, okay. Thank
Session.
you.
No, it's fine. Thanks, David. I need to
Thank you.
go.
Yeah, of course. Yeah, thanks. Right.
Yeah, it's wonderful when there are lots of questions at the end.
Yes.
We're happy
Yeah.
to-
So keep going. I'm
Yeah.
very sorry.
I'm here,
I'm-
no problem.
Thanks
Okay.
a lot. Yeah, I'm happy to take as many questions as there are, of course.
Yeah. So my question was about Taylor models. So do you plan to continue this work with other bases? Because I mean, here in the community, you probably notice that a lot of people work with Chebyshev or other kind of approximations.
Yeah, great question.
And yeah, sorry.
No, go ahead.
No, I mean,
I mean,
the thing is that there is, for example, in Julia, you probably know this Julia approximation community, like with Shihan Olven and other people. They do a lot of things, but non-rigorous. So I don't know if you plan to work together or.
Yeah, we did discuss it vaguely. We haven't managed to do anything yet. That would be fantastic. You know, I'm totally not an expert on the Chebyshev stuff. So, you know, if people want to work with us on that, that would be really great. Yeah.
Yeah. Oh, that's
yeah,
really good.
I mean,
thing to do.
you know, in a way, I think again, Julia is, you know, really an excellent language to implement that kind of thing in. Yeah. So one of the things I didn't actually say, I forgot to say, was, you know, there are some tools like Solya, that fantastic tool that tries to, you know, that reinvents the wheel in terms of, you know, the user interface. There's so much code for just sort of parsing input and etc., which you don't need any of that if you just use a language like Julia or indeed Python, right? So that's what the Sage Math project tries to do as well, of course. And so the point is, you know, in Julia, it's easy to define your own objects. Okay, the symbolic, yeah, as I showed, the symbolic side is getting much better as well. And so, yeah, I think Julia is really a fantastic tool to implement anything like that in, really. Yeah, so it would be great to have rigorous Chebyshev methods.
Okay, thank you.
Sure. Oh, yes, I should mention that the Taylor models, we also have multi-dimensional Taylor models. And that's what we're using for the reachability stuff, for the ODE integration. No, that's not true. But we do have multi-dimensional Taylor models. Yeah. Any more questions?
For your Taylor models, are they analytic Taylor models or they're like CK Taylor models?
So, well, it's a polynomial. It's a polynomial with a finite number of terms plus an interval remainder.
And so, but that's guaranteed to enclose the correct image on the real axis or on the complex disk?
Oh, I see. On this interval that you specify on the real line. Yeah. We haven't done any complex. That's true. We have not done any complex. We haven't worked on complex polynomials, so I guess it doesn't correctly work in the complex case. Yeah.
Just curious.
Yeah, good question. Yeah. That would be nice too. Yeah, there's a lot of things that would be nice. So, for example, like the interval root finding works on some complex. There's some support for complex functions to find roots in the complex plane, but it's not. You know, we haven't worked too hard on that yet, so it's not perfect.
Some of us are quizzing you to plan for future projects, right?
Yeah, definitely. Yeah, very happy to. Yeah, Hiroshi said I'll look forward to the book with full examples. Yeah, I also look forward to that book. I mean, that's sort of what this new website is supposed to be, but of course, it's far from being that. I did give a quite detailed tutorial, which was aimed at people who don't know interval arithmetic in JuliaCon 2020, and there's quite a lot of material there, which is on my GitHub page. You know, examples and things to how to use the packages, and we'll try and incorporate that into the website. But yeah, and a book maybe in the future.
Any other questions? Well, if not, let's thank our speaker yet again.
Thank you very much. Thanks.
David, thanks for powering through the technical difficulties.
Oh,
In
yeah.
the end, it was perfect, but I know
I'm
it was
glad.
stressful for you at the beginning.
Yeah, it was. I'm glad it worked. Yeah. Sorry about that.
Yeah, okay. Well, all right, everybody. Thanks again for coming. It was a great turnout today and a fantastic talk. And we can't wait to see you all again next week. So I'll stick around for a few more seconds in case anyone has anything else. But otherwise, see you all again next week.
Thanks, Mike.
Thank you.